I've heard worse.
You liar!
Come on, you pansy!
Have you ever thought about what it would be like to be missing one or both of your arms?
Victory is mine! We thank thee, Lord, that in thy mercy...
Come on, then. What?
Hollywood might make light of that situation, but for real people who have had their arms amputated, it is a much harsher reality. Until recently, these individuals have had their options limited to conventional myoelectric prostheses. While these devices can restore some function, they are only able to process a single control signal at once. This means that the user can only move a single joint at a time. Can you do anything moving a single joint at a time? Myoelectric prostheses have another drawback. They require the user to recruit muscles previously responsible for one type of motion, for example, shoulder movement as shown here, to control another often unrelated motion, like gripping. As you can imagine, this sort of control does not feel natural at all. Another option for prosthetic control involves a brain implant, which is installed to interpret the neurological signals sent from the brain to the muscles. Unfortunately, due to the fact that neural pathways degrade when not in constant use, these signals quickly become insufficient to elicit a response in the prosthetic device. Therefore, brain implants can only be used short-term. As you can tell, the options available for people in need of prostheses are limited, and they have the potential for causing great frustration. Fortunately, a new, amazing technology is on the horizon. Enter Dr. Todd Kiken and his colleague Dr. Gregory Dumanian. These two men, along with a staff of helpful researchers, developed a procedure called targeted reinnervation, or TR. Targeted reinnervation surgically transfers the residual nerves from the amputated limb to a muscle that, due to the amputation, no longer exerts any biomechanical function. Both the nerves responsible for motor control, called efferent nerves, and those responsible for sensation, called afferent nerves, are transferred during the surgery. To prevent interference, the nerves in the targeted muscle are removed. This also fosters the reinnervation of the muscle with the residual nerves. Once these transplanted nerves are established, the target muscle serves as an amplifier for their electrical signals. Using surface electrodes similar to those used in conventional myoelectric prostheses, these signals are read and sent into the processor, which ultimately controls the prosthesis. However, due to the amplification from the target muscles, these signals are considerably stronger than those used by myoelectric. As I mentioned previously, the TR procedure transplants both efferent and afferent nerves. However, only the efferent signals are responsible for controlling the prosthetic limb. In contrast to myoelectric control, the TR system produces multiple independent electrical signals. This allows the user to move all of the joints simultaneously, as demonstrated by one of the first TR patients, Jesse Sullivan. If this degree of control over a prosthetic limb is not exciting enough, the afferent nerves transplanted during the TR procedure have the potential for creating sensory feedback for the prosthesis. The ultimate hope of this targeted sensory reinnervation is to connect sensors located on the prosthesis to stimulators located on the target muscle. These stimulators would activate the afferent nerves, ultimately allowing the patient to feel with the prosthetic limb. Who knows where this kind of technology might take us? Who knows how authentic we can make a prosthetic limb? I hope you've enjoyed this brief description of targeted reinnervation. If you would like more information, you should look for articles by Todd Kiken and his associates, or you should check out the Wikipedia page devoted to targeted reinnervation. Until next time, I'm Kellis. Thanks for watching.